Hi, in this video we're going to be discussing our tutorial 3 questions. So tutorial 3 is on our timer and as well as our serial interface. Okay, so the first question is basically telling us that there is a new microcontroller from ARM called the Cortex M0, okay, that is running at 20 megahertz. Okay, and this controller doesn't have a PWM capability, but it does have a 16-bit timer module. Okay, that behaves very much like our periodic interrupt timer in the Cortex M0 Plus. Okay, so if you have gone through the e-lecture, you would have known that basically how the PIT works is you put in a start value, okay, which is called a timer start value, and then it starts to count down. Okay, when it hits 0, okay, so 0 is basically the final count. Once it hits 0, it can generate interrupt first. Okay, at the same time, it will reload back with the same value. Okay, and you can carry on counting. Okay, if you wish to change the value, okay, you can update a new timer start value in the ISR. Okay, so that is basically how your periodic interrupt timer works, okay, in the ARM. Similar, and this controller here is having a similar uh, behavior. So now design the pseudocode to generate a 50% duty cycle PWM signal using this timer interrupt. Okay, so basically if you look at the solution as given, what we need to do is to first set the GPIO pin to 0. Okay, so I take a particular GPIO pin. So since we do not have a PWM module, okay, generally when you have a PWM module, the hardware is already configured that certain pins are tied to this PWM capability. And in this case, we do not have that, so we are free to use any GPIO that is available. And what we're going to do is on this pin, we're going to initially set it to low. Okay, yeah, so we're going to initially set it to low. Let me see here. Okay, okay, so let me erase that. Okay, so initially it's going to be low, and we're going to set the timer start value to 0x7FFF. Okay, so what is going to happen is the initial start value is 0x7FFF. Okay, and we're going to enable interrupts for the timer module. Okay, so once I say start timer, what happens? Okay, the timer hardware will start to count down. Okay, and when it hits 0, okay, so this is 0. When it hits 0, it will jump to this ISR. Okay, and when it jumps to the ISR, what I need to do is toggle the PWM GPIO pin. So I will toggle it. Okay, and then it will stay for how long? For the same duration. Okay, why? Because the behavior of the periodic interrupt timer is it will automatically go to the it will automatically reload the TSV value into the timer. Okay, so this is the TSV timer timer start value, and it will automatically reload this value into the counter register or timer register, and again begin the countdown. Okay, so it will be low for 0x7FFF ticks, okay, or counts, and then it will again go back toggle, and then it will stay at that logic for another 0x7FFF counts, and then the next ISR it will toggle back. So I'll continuously be doing this. Okay, so this 7FF is just a random value. If you had chosen a smaller value, okay, so if instead of 7FF you had chosen 0xFF, what happens? It's just that I toggle faster. Okay, I toggle faster, but the duty cycle is still the same, 50% duty cycle. Why? Because whenever I interrupt, I will always reload back with the same value for the from the TSV register to the timer or counter register. Now, what if I want a 75% duty cycle? Okay, so in that situation, basically what we are saying is we want to be high a bit longer and low a bit shorter. Correct? Something like this. Okay, so what I need to do is I need to figure out two TSV values. Okay, so this is TSV1 and this is TSV2. Okay, and this is the whole T. Okay, and these two values must be such that, okay, TSV1 over TSV1 plus TSV2 must be equals to 0.75. Okay, so I can choose any values, okay, but it must satisfy this condition so that I am able to fulfill a 75% duty cycle. Okay, then of course it means that in your ISR, you also need to keep toggling between two TSVs, correct? Currently with 50% duty cycle, the same TSV value is used again and again. Okay, so I just need to toggle the pin. But now that I'm going to switch between two different TSV values, I need to make sure that the TSV values are also updated correctly every time an interrupt happens. So at one instance, it will be TSV1, then it will be TSV2, and then I keep cycling through. Okay, so that is how you can still use the same approach and then create a duty cycle that is other than 50%. Okay, so that is your first question. Now, what is the period of the waveform? So the period of the waveform basically relates to how long it takes. So as we saw just now with our current code, it takes 0x755, so 7FFF counts to generate the interrupt, and then I'll toggle again. Okay, for the same duration of time after that. And since I have a 20 megahertz clock, the period of the clock is 15 nanoseconds. So 15 nanosecond is for one clock period, and I need 0x7FFF clocks to hit a interrupt. Okay, so this duration here is 1.638 millisecond, and the period is double of it. That is the whole period of the PWM waveform. Okay, so as I think it's quite obvious that the period does not in any way affect the uh, average voltage that the signal will see, because as long as it's 50% PWM, the average voltage will always be half of the voltage for 0 and 1. Okay, so if your logical 1 is currently, let's say, 5 volts, then this will always be 2.5 volts, regardless of whether it's high frequency or low frequency PWM. If the duty cycle is 50%, your voltage, the average voltage that the device will see at the output pin is always a 2.5 volt or 50% of the logical 1 value. Okay, now let's look at this question. Another microcontroller, Latex M0, doesn't have the timer module and wishes to still generate a PWM signal. Okay, how can we still do it? Okay, so this is basically a simple pseudocode, very similar idea, except that what we are doing is we are, okay, so I think there's one extra F here. Okay, so 0x7FFF, and from this value, the starting point, we will decrement. So we have a variable, okay, counter, and this value is 0x7FFF, and what I will do is I will decrement, and I'll keep counting down till I hit 0. Once I hit 0, I will do the same toggling, and I reload my variable, and then I will do again. Okay, so very simply, very much similar to what we saw just now. But what is the main difference is that in this case, you are explicitly doing the count in software. Okay, whereas in the earlier approach, we were using a hardware based timer. Okay, so that is actually a big difference, because when you use a hardware based timer like just now, okay, as you can see in this while one loop here, you are free to do anything you want. Okay, and the timer interrupt when it triggers, then the pin will be toggle. Okay, so in this while one loop, you are actually free to do whatever you like to do. Okay, and the timer interrupt will still carry on as per normal. Okay, whereas in this approach, okay, since it's a software based timer, you are very much focused on this, correct, and you can't really do anything else meaningful. Okay, so that is a drawback. And of course, if this same code, while it is running, I also have maybe other interrupts in the system. Okay, and if those interrupts were to be triggered anywhere while I'm in the while one loop, those interrupts will take time. Okay, so when I come back, okay, this time difference could always vary. Okay, because in between I could have had interrupts from maybe a push button or a serial or something else. Okay, so it is a very ineffective way of generating a PWM signal if you really want a very accurate signal with a specific duty cycle. Okay, because the time difference between the start value and the time you reach zero can always vary if there are other interrupts in the system or other things you want to do in between. Okay, so it's not a very effective way of generating a PWM. Okay, so question 2 is on serial interrupts, and for our project we are required to use serial interrupts. Okay, and you can always refer back to our lecture slides, okay, where most of the code is already given there. Okay, and from there you can adapt to your lab exercise, and from there integrate to your project. Okay, and this pseudo code shows you a implementation. Okay, so as you can see, we have a serial ISR over here, which will be triggered whenever data comes in, and in the main uh, function here, you basically keep doing this check. Okay, I think what is missing here is actually a while one loop. Okay, so you need a while one loop over here. Now, discuss some issues with the implementation. Okay, so let me rewrite the while one loop. Okay, so this while one loop will make sure that we are always continuously processing the data that is received. Okay, now what are some of the issues with this implementation? Okay, so as you can see, this here ISR will automatically be triggered. Okay, whenever there is data that is coming in or that's been received by the UART module. Okay, now in the main loop you are checking for the new data flag. Okay, so I will set this RX new data to 1 whenever data has been received, and if there is new data that has been received, then I'll process it. If not, I'll do other things. Okay, so one of the things that you can see quite clearly is if I miss this check and after I complete this check, then the ISR is triggered. Okay, then what would happen is I would have already been busy doing other things. Okay, so and these other things could take very long. Okay, and because of that, it will not be an immediate response to the data that has just been received by the controller. Okay, so I may receive it. So if I were to draw a timeline here, so I can say that I do the if check here. This is the if check I'm talking about. Okay, and rest after the if check, I see there's no data, and then I go and start the else. So okay, so over here I do the else, and at this point of time is where the data is received. Okay, so the serial ISR is triggered here. Okay, so I need to do the whole else thing, which is the other things. The doing the other things. After that, only I come back to the next iteration of the if. Okay, so this time duration, this t, can be very long. Okay, and with this t being very long, I can or basically means that I will not be able to process the data the moment it comes. I need to wait until the next iteration of this while one loop, and then only I'm able to process the data. Okay, so that is one issue. And of course, another thing is, what if there are multiple interrupts during this time? Okay, so in this same time duration, what if there are multiple interrupts coming in? Okay, which means that the data which is stored inside this variable RX data is overwritten each time, okay, with the new data that has come in. Okay, so you also have the potential problem of losing information because every time new ISR is triggered, I override the old data. Okay, so these are two of the issues, okay, which you can see over here. And with this, basically you see that it is not a very effective solution, okay, because you are still having to have a delayed response to the data that is coming in. Okay, and at the same time you can lose the data, okay, if you are not able to process it fast enough. Okay, so the other thing is global variable RX data is declared as volatile. How does it affect the behavior of the robot? Okay, so let's go back to the code here. So let's assume that right now, okay, I have the interrupt, correct, and when I do the if check, the RX new data has already been set, correct. So at this point of time, the RX new data is equals to 1. So I'll come inside this code here. Okay, and inside this code, what do I see? Okay, first I will do this check. If Rx new data equal to 0, and then I move robot forward, correct? So rightfully, this data packet that I receive would have instructed me to move the robot forward. So let's assume that in this point of time, I call the move forward. And move forward is a function call. Okay, so we do not know how long it may take. So it may take some time before I can finish this move robot forward. So what is the potential issue? The potential issue is while I'm in this function, another interrupt is triggered. Okay, another interrupt is triggered, and then what happens? Okay, the Rx data is updated. Okay, Rx data is updated with a new value. Okay, and so when I finish this function and I come out, I'll do the next if check. Correct, and if the Rx data at that point of time was 0, 1, then what would happen? I would also execute this line. Correct, so I'm moving forward, and at the same time I'm also going to be moving right. Okay, so this again, maybe this is how you want it to be. Okay, or it could have just been a side effect of the way the code was written. Okay, so these are small things that we need to be careful about, okay, in designing our architecture, because Rx data is declared as volatile, correct, which means that I will always be updating it. Okay, and always be reading from it, okay, whenever I need to do a check. So in this case, your robot may be executing two or multiple operations with just one iteration of the if. Okay, and again, this may or may not be your intention. Okay, so that is a potential side effect. Okay, so it all depends on how the low level drivers are written. Okay, so sometimes maybe the low level drivers are written such that whenever a new robot command is received, I will stop the old command, then I'll do a new command. Okay, but if I'm written in a way that the old command may still be carrying on while a new command is processed, then you may have some funny behavior. Okay, so these are some of the issues that we need to be careful about. Okay, so one last thing is, if this is not the intended behavior, okay, and I want to make sure that if I go inside this if, okay, I only process one of this move functions, the easiest way to sort of solve this, okay, is to just replace all this two if here with the else if function. Okay, why? Because if I replace with else if, the moment one of them is satisfied, I will automatically skip, okay, to the end. Correct, so that is one easy way of sort of resolving this if that is not the intended behavior. Okay, the last question or the next question here is on circular queue. And basically what circular queue does is basically it creates a buffer that goes in a circle, and you have a certain number of elements, and then what you do is you have two pointers, a head and then a tail. Okay, and basically if you look at the lecture slides, what you see is whenever there is new data, I'll update and I'll move the tail. New data, I'll update and I'll move the tail. Okay, and whenever I want to read, I read from wherever the head is pointing to, and then I update the head and so on. Okay, so I think in the lecture slides we have gone through all of this, so I'll not repeat that. Okay, and the behavior, I mean the code is still fulfilling the same objectives. The only difference is now I'm using a circular queue to manage my data. Okay, now basically what you see here is in the interrupt, I check whether the queue is full. If the queue is not full, I enqueue the data. Okay, that means I take the data, put it onto the queue, then I adjust my tail pointer. And similarly in the main function, okay, so again there is a supposed to be a while one loop here. So in this main function, what do I do is, as long as the queue is not empty, that means there has been some new data that I've received, I will dequeue the data, okay, and then process it. Okay, so that is basically what this circular queue does for us. And what does it actually solve? Okay, so the main thing is, firstly, you solve the issue of overriding data because you have a circular queue, a circular buffer. Okay, and this circular queue or circular buffer, basically what it does is it can have multiple data entry points, okay, or multiple, it's basically like an array, correct? So you have a lot of data that you can save, and because of that, you are able to handle multiple interrupts while you are still busy doing other things. Okay, so if you look back at the same timeline, okay, if after the if check I go and do the else, okay, and during this period of time I can have multiple interrupts, doesn't matter, each time the interrupt comes in, okay, I will still be able to update the buffer and keep the data. Okay, now uh, what is the potential issue is if the interrupts happen too frequently. Okay, that means or in other sense, the do other things takes too long, and many interrupts have already happened by the time, there may still be a potential issue where I have filled up all the space in the circular cube, correct? Okay, so that is a potential issue that we still have to be concerned about. Okay, um, and then of course, uh, if you look at it, the way the code is written is, each time the queue is not empty, I only dequeue once, okay, and then I do other things. So if let's say there were 3 interrupts that were triggered, when I come back to the next if iteration, I would have dequeued the first data, correct? I would have dequeued the first data, and I would have processed it over here, okay, but after processing it, I would have gone and do other things. Okay, so there are still other commands that are in the queue that have not yet been processed. Okay, so this if statement only processes one uh, data in the queue at a time. Okay, so even though many interrupts may have happened, I'm still processing it one at a time. Okay, so this is also another issue that you may want to deal with, okay, in the way you write your code. Okay, okay, so how can I resolve this issue of trying to make sure that data is processed as fast as I receive it? Okay, that means the moment a data comes in, I know I'm able to capture it. So the serial ISR knows that I can capture the data, okay, and I can keep the data safely through the circular buffer. So all of that is good, but processing the data is still being delayed. Still being delayed. And what can I do? Okay, so in ARM we have this set pending IRQ option where I can trigger interrupt. So what I'm saying now is uh, in the timeline, okay, so this is the if statement, okay, and then I skip it and then I go to the else, correct? And while I'm in the else and doing other things, okay, at this point of time an interrupt comes in, a serial interrupt. So this is the serial interrupt, and now currently, even though I capture the data here, I need to wait until the next if, okay, but now what I'm saying is once I capture the data, I go and trigger another ISR, okay, so I will jump to another interrupt to process the data, okay. And why this works is because I'm able to generate an interrupt, I will still be able to bypass whatever I'm doing in the other things and go and process the data very quickly, almost immediately. Okay, how does this work? Okay, so you can think back at our push button. Okay, so our push button interrupt in the lab that we did, okay, is basically to capture an external event. Okay, so we can say that we want to capture a rising edge or a falling edge or whatever. But since we have a set pending IRQ, this set pending IRQ is uh, a way of overriding the hardware trigger and triggering it through a software means. Okay, so a set pending IRQ can actually help us to trigger the same interrupt service routine as if the hardware was generating it. Okay, but I'm actually doing it through the software. Okay, so you can try to integrate back the interrupt push button functionality, and in this situation, instead of having a physical transition on the pin, the set pending IRQ actually can give you the same kind of response, because the moment set pending IRQ is detected by the code or by the controller, you will actually jump to the ISR to process it as if it happened physically. Okay, so that is one way of generating a software interrupt to handle the data that was received. Okay, so that is one option. Of course, there are maybe other options that you can think about, and as we go towards multi-threaded design, you can also say that I can trigger a thread to handle the data. Okay, so that is something that we will be exploring as a more efficient solution, where in the timeline, okay, at this point of time, the serial interrupt is triggered. Okay, and then what happens is one of the threads. Okay, so I will have a UART thread. Okay, and the UART thread will be waiting for the data. So I need to send some notification. Okay, some notification that will allow, or that will let the UART thread know that new data has been received, and I can now process it and do what I need to do. Okay, so we will be exploring this, okay, in future lectures and in the labs as well, how you can have one task or one interrupt uh, signal another task or to perform some action for us. Okay, so that is those are things that we will be covering very soon, okay, in the future lectures. Okay, so that's about it. So thank you. Okay, so if you have any questions about this tutorial, please feel free to ask me. Okay, if not, the lab that you had done on the UART, okay, is important, okay, for the Bluetooth interface. And look out for my next video on the tutorial 4, okay, which is on the um, introduction to the RTOS and states of tasks and how they can switch between the tasks as you're executing. Okay, thank you.